So let's spend some more time on determinant. And so some properties of determinant. Say, actually I don't like this blue, so it would be nice if I can set the default for the colors, but I don't know that well. So you must be now quite familiar with how to calculate the determinant. And so this is a general case, so it doesn't really matter which row or which column you expand with the four-factor matrix, but let's choose this as this row to calculate the determinant. So determinant A is, so actually you can do A11, C11, A12, C12, A13, C13, right? And C11 is minus 1 to the 1 plus 1 M11, which is the minor is a determinant of a matrix obtained by deleting the first row and first column, right? So M11 will be, you delete this first row, first column, so this is M11. So this is, oops, sorry. So minus 1 to the 1 plus 1 is plus, right? And so this is A22, A23, A32, A33. Let's just write it down that way for now. C12 is minus 1 to the 1 plus 2, M12. So that is the minor obtained by deleting the first row and second column. This and this, so. And minus 1 to the 1 plus 2 is minus. So this is minus of A21, A23, A31, A33. I just need to find some space. And C13 minus 1 to the 1 plus 3, M13 is minus 1 to the 1 plus 3 is plus 1, correct? And M13 is the minor obtained by deleting the first row, third column, so this is it. So A21, A22, A31, A32. So you can just substitute this into this formula, A11, A22, A23, A32, A33, A12. C12 is minus, so we can put minus sign here. And A21, A23, A31, A33, plus A13, A21, A22, A31, A32. Now we can calculate the determinant of 2 by 2 for those minors. A11, you have A22, A33 minus A23, A32. And minus A12, we have A21, A33 minus A3, A23, A31 plus A13, A21, A32 minus A22, A31. So how many terms do we have? You can count 1, 2, 3, 4, 5, 6 terms, right? So let's just rearrange plus and minus terms. So A11, A22, A33. And here, in the second term, this contributes to the positives. So that is A12, A23, A31, plus A13, A21, A32. And we have minus A11, A23, A32 minus A12, A21, A33 minus A13, A22, A31. And we might be able to extract. Extract means you pull it out, 추출하다. So let's try to express some properties by just looking at which term is positive, which term is negative. So let's try to find the common factors first. So we start with 1, 2, 3, right? So we actually arrange the terms, component, the product, such that the first index is 1, 2, 3. The second index, second term is 1, 2, 3. 1, 2, 3. So this is common factor. We arrange the each terms according to 1, 2, 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. Then take a look at the column index, second index. So this is 1, 2, 3. 1, 2, 3. So I'm going to put the positive sign over second index. So 1, 2, 3 is one collection. And 2, 3, 1. If the second index is in the order of 2, 3, 1, it also contributes to the plus, right? So let's put 2, 3, 1. And 3, 1, 2. So 3, 1, 2. That gives positive contribution, positive terms. How about negative terms? 1, 3, 2. So 1, 3, 2. Or 2, 1, 3. 2, 1, 3. And the last one, 3, 2, 1. 3, 2, 1. So can you get something in common with this collection and this collection? Anybody can find out what is common for these three terms? 1, 2, 3, 2, 3, 1, 3, 1, 2. Or the negative terms also have this. Can you arrange 3, 2, 1, 1, 3, 2, 2, 1, 3. So you can, let's try to figure out what are the common factors for the positive terms and negative terms. 1, 2, 3. So what's the common thing? 1, 2, 3, and 3, 1, 2, or 2, 3, 1. 1, 2, 3. Yes.
I think they are kinds of families. Like 2, 3, 1 is when you change the numbers, well, numbers 1 to right side of 2, 3, and 2, 3, 1 is, I think they are families. And 2, 3, 1, 2 means is change 3 to the left side of 1, and 3,
You're getting close. So this is very close. Okay. What you can obtain is 2, 3, 1. So you interchange 1 and 2. So you have 2, 1, right? And then you again interchange 1, 3, and you have 2, 3, 1. So if you interchange two numbers, again number twice, then you obtain 2, 3, 1 from 1 to 3. The same thing. If you interchange with 2, 3, then you have 1, 3, 2, right? And then you interchange 1, 3, 2 with this 1 and 3, then you have 3, 1, 2. So you interchange the neighboring numbers twice from 1 to 3, then you obtain this whole family list. And we call this even permutation. Right? Even permutation of 1 to 3. So those numbers are actually even permutation. 1, 2, 3. On the other hand, 1, 3, 2 can be obtained from 1 to 3 by just changing 2 and 3 ones. Right? Or 2, 1, 3 can be obtained from 1 to 3 by interchanging 1 and 2 ones. Right? And 1, 2, 3, 2, 1. How many times do you have to change? 3, 2, 1. You change once, 1, 2, 1. Twice, 3, 1. And then third time, 3, 2. So this time is obtained by 3 times interchanging of neighboring numbers. So this is called odd permutation. Odd permutation of 1, 2, 3. I don't know if there is a Korean expression. Permutation. 조합? 기조합? 우조합? Permutation. Permutation is permutation is the arrangement of numbers. So you change it twice. Or you can write this way. Keeping out this term. So if the second index of 3 product arranged in even permutation 1, 2, 3, 2, 3, 1, 3, 1, 2, then you have positive signs, right? Or it is written in 1, 3, 2, 2, 1, 3, or 3, 2, 1. So second index is arranged into the odd permutation, you have minus sign. So let's just try to figure out, write down this way. So now we figure out the general prop rules. So we have 1, 2, 3. counterclockwise arrangement. Right? 1, 2, 3, or 2, 3, 1, 3, 1, 2. So counterclockwise arrangement of 1 to 3 is an even permutation. Or 1, 2, 3. So this is called counterclockwise. Or if you change into clockwise arrangement of 1 to 3, it's 1, 3, 2, 3, 2, 1, 2, 1, 3. That's the odd permutation. One, two, three. 1, 2, 3. And this is called clockwise. Then, so it's a very simple picture. Then you can actually write down the determinants terms by using this. Determinant A can be written as, say, A1, A2, A3, A1, A2, A3, A1, A2, A3, minus A1, A2, A3, minus A1, A2, A3, minus A1, A2, A3. So we need to fill this second index without actually calculating the determinant, because we figured out if the second indices are arranged into even permutation, it gives a positive sign. It is arranged into the odd permutation, it gives a negative sign, right? So let's figure out. So the first arrangement will be even, right? So can you call something even? You arrange this way, right?
1, 2, 3.
Okay, very good. 1, 2, 3, and 2, 3, 1, right? 2, 3, 1. Third terms? 3, 1, 2, right? How about negative terms? 1, 3, 2, right? Very good. You're getting good. 3, 2. And second case? 3, 3, 2, 1. Very good. And 2, 1, 3. 2, 1, 3. You're getting very good. So we know the rule, right? For calculating determinant. Then for 3 by 3, you only need to be concerned about if the second indices are arranged with even permutation or odd permutation. So, but still we have to write down 6 terms, right? So it will be nice if we can write down into a single expression. So in order to do that, let's introduce some concept. Copying I'll give you a few minutes to do that. Since we figured out that determinant can be actually written down with the permutation for the second indices, right? So this arrangement of writing down 6 terms is actually same as, okay, so if you haven't finished, let's try to introduce function. So let's introduce the special function called epsilon ijk. It has a name, Levi-Civita. Equal symbol. So Levi-Civita is an Italian mathematician of the 19th century. So he introduced this concept, and he found that it's very easy to calculate the determinant. So for example, epsilon 1, 2, 3 is epsilon 1, 2, 3. So I'm going to write down this way, 1, 2, 3. For example, clockwise, counterclockwise. So this is a plus, this is a minus. So epsilon 1, 2, 3. Plus or minus? Right. Epsilon 3. So 1, 2, 3. 2, 3, 1. Plus 1. Very good. Epsilon 3, 1, 2. Plus 1. Very good. Epsilon 1, 3, 2. 1, 3, 2 is minus 1. Epsilon 2, 1, 3. Minus 1, right? Epsilon 3, 2, 1. Minus 1. Epsilon 1, 1, 0. 1, 1, 2. 0, right? Etc., etc. Then determinant can be written down. Then determinant A can be written down as I, J, K, epsilon I, J, K, A1I, A2J, A3K. So our previous expression of this single expression, epsilon ijk, a1, I, a2, j, 3k. So let's actually do this for 3 by 3 because it's very important to understand this abstract thinking. So previously, we actually expanded the determinant and obtained 6 terms, right? 3 positive sums and 3 negative terms. And then we found that there is some correlations in the second indices of the term. And then if the second indices are arranged into even permutation, you assign plus sign. If the second indices are arranged into odd permutation, you assign minus terms. And then by introducing this Levi-Civita symbol, we can actually write down this determinant into single terms. So, but a bit too difficult, right? Actually. So some of this introduction of new terminology might cause you so-called mengung to some of you, right? So I'm going to just write down, go back to the previous expression again. So just be patient. So let's expand this. I, J, K, epsilon I, J, K, A, N, Y, A, 2J, A, 3K. So I can be starting with the 1, right? So epsilon 1. So there are how many terms? I can be 1 to 3. 27 terms actually is 1 to 3. Right? So A1, 1, 1, A1, 1, A2, 1, A3, 1. Epsilon 1, 1, 2, A1, 1, A2, 1, A3, 2, plus epsilon 1, 1, 3, A1, 1, A2, 1, A3, 2. So I have to write down 27 terms. But actually we don't have to, because when I and j are the same, it's all 0, right? So actually I don't have to write down 27 terms. So I just put it there, but this will all 0, right? So actually we don't have to expand 27 terms. So when I is 1, j has to be either 2 or 3, right? So let's do it more wisely. So epsilon 1. Then possible combination of j, k is 2, 3. So 2, 3, A1, 2, A2, 2, A3, 3, plus epsilon 1, 3, 2, right? That's the only non-zero terms. A1, 1, A2, 3, A3, 2. Second term, when I is 2, jk can be either 1 or 3, right? Otherwise, it's all 0. So out of 27 terms, we know that 21 is all 0 when I and j are the same, or I and k the same. So we don't have to write down all 27 terms, but only non-zero terms. So when I is 2, j can be 1, k can be 3. So A1, 2. I think it is has to be 1, right? A2, 1, A3, 3, and epsilon 3, 1, A1, 2, A2, 3, A3, 1. And I can be 3. Then jk can be either 2 or 3. So 2, 3, A1, 3, A2, 2, A3, 1, or epsilon 3, 1, 2, A1, 3, A2, 1, A3, 2. Now we only need to determine the sign. So epsilon 1 to 3 is what? This is plus 1, 3, 2. I will write down this way. 1, 2, 3. So this is plus, supposed to be plus, and this is minus. So 1, 3, 2, which is minus. 2, 1, 3. 2, 1, 3, minus, right? 2, 3, 1, plus. 3, 2, 1, minus. 3, 1, 2, plus. So we obtain the same expression as before. So just arrange plus terms. A1, 1, A2, 2, A3, 3, plus A1, 2, A2, 3, A3, 1, plus A1, 3, A2, 1, A3, 2, minus A1, 1, A2, 3, A3, 2, minus A1, 2, A2, 1, A3, 3, minus A1, 3, A2, 2, A3, 1. So at least we found a systematic way of calculating the determinant, and this is very convenient. So if it is greater than 4 by 4, in the previous quiz, actually, we calculated the 4 by 4 determinants by extending minus, right? But there is a room there you can use this new knowledge, but some of you still write it down, so let's try to see if how, but we have three indices. That is very easy to determine, the even permutation and odd permutation, right? But how about if you have 4, for example, 1, 2, 3, 4. How are we going to arrange? Because this doesn't work actually. So 1, 2, 3, 4. So even permutation is you change it twice, even number of times. So neighboring numbers. Then is even or odd interchanging neighboring numbers we call odd permutation. So let's try to so how many different possibilities do we have? For example, if we have 1, 2, 3, how many terms do we have? I, j, k. I, j, k. The first index can have 3 choices, right? So once we choose 1, then second index has 2 possibilities. And third choice is 1. So there are 6 terms, right? So if you have 4 different indices, so if I, j, k, l, so first index we have how many choices? 4, 3, 2, 1. So how many? 3, 24. So this is actually 3 factorial. This is actually 4 factorial. Very interesting. So we have a 3 factorial possibility permutation. So half of the 3 factorial is even, and half of the 3 factorial is odd. And in the 4 indices, we can have same, 24. So we can actually introduce I, j, k, l as plus 1 even, minus 1 I, j, k, l odd, otherwise. So let's try to write down the even permutation of 1, 2, 3, 4. So Levi-Civita symbol can be actually extended into higher dimension. So let's try to figure out how many even permutations you can obtain from 1, 2, 3, 4. 12, right? So let's do some practice. This is just algebra. So start with 1, 2, 3, 4. Even permutations. we need to change 2, right? So you interchange this 2, right? Then this 2, 1, 4, 3. And you interchange this and this. What we have? 4, 3, 2, 1. That's even permutation. And you change more, etc., etc., etc. And odd permutation, you just interchange once or 3 times. Odd permutation, for example, you interchange this 2. This is even, odd, 1, 3, 2, 4, etc. So at this time, it will be a good, point to give you homework to find 12 even permutations of 1, 2, 3, 4, and 12 odd 1, 2, 3, 4. Can you do that, right? So change twice, 4 times, 6 times, 8 times. Then you can obtain even permutations. So you find out 12 even permutations and change once, 3 times, 5 times, then you obtain other permutations. There are going to be 12. And then it's going to be a very nice homework. So this is homework. And another homework is a bit vicious. You need to copy. So actually finding the even permutation, so only 12, so you can find out. And only 12 odd permutations, so only 24. So if I expand to 5, how many do we have? 120, so it's a little too much, right? So let's just focus on 4 by 4. Another homework I said even 4, 3, 2, 1 is not even. So you change your neighboring numbers twice. Okay, you to assign you is calculate the determinant of this matrix. A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, A41, A42, A43, A44. So find determinant A. This one homework, and check if so you already obtained the epsilon ij KL previously, right? Even odd permutations, and so check out if these two results agrees. So that's your homework. Very nice homework, right? And actually, this approach is you can use computer program to calculate the determinant. It's very easy to find the function even or odd commutations, and then you can just ask the program to sum over this product with the coefficient. Then actually that's how we calculate the n by n determinant. So for n by n determinant, I think I made a mistake here. So we define, so ijk is running out of indices. So I'm going to introduce new epsilon I1, I2, In plus minus even commutation they're all different odd commutation 0 otherwise. Then if A is given by Aij, which is n by n determinant, then determinant A can be written as I1, I2, In, epsilon I1, I2, In, A1, I1, A2, I2, In. So that's a more general formula for the n by n determinant. And that is how usually we calculate the determinant using computer. So it's more convenient. But if it is less than 4 by 4, maybe using the minor expansion, minor 4 factor is easier. But it is up to 24, right? But if it is larger than 5 by 5, then expanding by 4 factor matrix is not very convenient either, right? There's a lot of calculations, and then maybe you have to rely on the computer. Then this formula is more convenient for that. But luckily, I'm going to focus on to 4 by 4 for quiz, final, whatever. Maybe we can take a break for a few minutes and continue. We introduce n by 1 column vector as a cat vector, and by 1 column vector is denoted as x and called as cat vector, or denoted is the same as written down. And most of the cases we are going to consider the real numbers, but for generality, let's consider that this x1 to xn is complex numbers. Say x1, xn are complex numbers. So So anybody who never heard about complex numbers, raise your hand. 복소수 못 들어본 사람. Complex numbers. So you know about that, right? So for example, xi is another good combination. xk. xk is ak plus ibk. So ak, bk are all real numbers. K are integers, set of integer. I is square root of -1, or I square is -1. Then we can define complex conjugate ak minus ibk, which is called complex conjugate of xk, which is called star. So complex conjugate of x is called xk star. And you just change the sign of in front of A. In Korean, it's called kolle복소수. When I was a student, it's called 공액복소수, but I think these days it's called kolle복소수. But so we are going to use complex conjugate. So interesting thing about complex conjugate is we are going to spend more time with the properties of complex numbers in the second semester, but let's just briefly study what we need for this semester. Then if xk is ak plus ibk, xk complex conjugate is ak minus abk. So xk complex conjugate, ak plus ibk, ak minus ibk, and ak, ibk, ak minus ak, bk, I minus I, bk, bk. So these two cancels each other, and we have ak square, bk square. I guess most of you know this properties already. So from this, when we have a ket vector, so ket vector is just a notation for the column vector, 1 by 1, n by 1 vector. Then we define bra vector, complex conjugate. It is named called bra vector. So bra vector is actually 1 by n row vector. It's 1 by n row vector. So bra vector is a row vector, and ket vector is a column vector. And actually it is obtained from this. What happens if you transpose a column vector? If you transpose a column vector, the column becomes row, right? But there's one thing more, because this bra vector has a extra property. This complex conjugate, right? So you obtain with a complex conjugate. And this actually transpose complex conjugate is called adjoint. Adjoint operation. So adjoint is in transpose and complex conjugate. This is called adjoint. And especially this is called dagger. Because if you have a magnifier, and if you look carefully this, you look like this dagger. So mathematicians call this adjoint operation is also sometimes dagger. Then so say x then you can define bra vector, which is x1, xn, y, y1 complex conjugate, yn complex conjugate. Then bra vector and cat vector can be multiplied together to form an inner product. So x, y. They form a scalar, right? So if you multiply by row by column, what do you get? 1 by 1, right? This is the scalar. So inner product is sometimes called the scalar product. x1 star y1, x2 star y2, xn star yn. So if you have a bra vector and cat vector, then you can form an inner product between bra vector and cat vector to form a scalar product. You obtain the scalar. What if you interchange the order? That's xy's, right? So on the other hand, previously xy, we can also change the order yx. We obtained xy. Right? If we have a yx, y1 star, yn star, x1, xn. So y1 star, x1, y2 star, x2, yn star, xn. It's actually x1 star y1 complex conjugate, x2 star y2 complex conjugate, xn star yn complex conjugate, same as this, x1 star y1, xn star yn complex conjugate, same as xy complex conjugate. So when you change the order, then you just put the complex conjugate. But if the order entries are real numbers, then they are the same. So they are different only when they are complex numbers. So am I going a little bit too fast, or is it okay? So maybe you can spend a few minutes why this strange forms, notations are called cat vector and bra vector. And actually it's from English. In English, what this is called what? In English, bracket. How about this? Karo. Parenthesis. Paren. Maybe I think it's E. Parenthesis. How about this? Brace. Let me just check the spelling. Parenthesis. E-A-R. I think it's A, but parenthesis. Yeah. Parenthesis. E is parenthesis, brace. So we divide by half, bracket, so this part become bra vector, this part become cat vector, bracket. The cat vector and bracket, bra vector was introduced by 1925, 1920s, by Peel, Andurian, Maurice Dirac. He's an English physicist who got the Nobel Prize in 1925. He was 21 years old when he got the Nobel Prize. So he made a very profound contribution to the quantum mechanics, and then he introduced this bra vector, cat vector notation from the English. And so inner product actually makes you scalar. But there is another product called outer product. Simply y1 product, x2, y2 complex conjugate, x2, yn complex conjugate, xn, y1 complex, xn, yn. So outer product is a way of enlarging the matrix dimension. So outer product is n by n. So for example, say x 1, 2, y 3, 4. So what is xy? So inner product can be 1, 2, 3, 4, 11, right? Or yx 3, 4, 1, 2, 11. So in this case, they are the same because it's a real number. How about xy? 1, 2, 3, 4, 3, 4, 6, 8, right? How about yx? 3, 4, 1, 2. 3, 6, 4, 8. So they are not same, right? So in general, the output product is not commutative. So in general, but there is interesting property between inner product and outer product. So in general, if you interchange the order, they are not the same, right? Okay. Some simple example: x 1 2, y 3 4, z 5 6. And let's try to calculate x, y, and z. So this is a uniform out product of cat vector x and y, and then we multiply by n matrix to z, right? And see what happens. So in this case, so this is 1 2 3 4. 5 6 3 4 6 8, right? 3 4 6 8 5 6. The first term, 15 plus 24, 39. The second term, 30 plus 48, 78, correct. How about this? Interesting thing is, x is 1 2, y z 3 4 5 6. So if you do this, what do you get? 15 24 39. So it turns out that 39 78. So this is very simple but very interesting properties of inner product and outer product. So in general, I can have, this is amazing, isn't it? So inner product, outer product can be written down this way. So this is actually the beauty of using the cat vector notations. So So product of outer product and inner product is associative. We have x, y, and z, same as x, y, and z. So this is very interesting property. Let's check. It takes a little while. So x1, xn, y, y1, yn, z, z1, zn. So xy is x1, xn, y1 complex conjugate, yn complex conjugate, right? So it can be written down as x1, y1 complex conjugate, x1, y2 complex conjugate, x1, yn complex conjugate xn y1 complex conjugate x2 y2 complex conjugate xn yn complex conjugate by definition of the output product. And then we now multiply C. So X, Y, Z. Do I have enough space? C1, Cn, right? What do we have? You multiply this and this, right? So we have x1, y1 complex conjugate to g1 plus x1, yn complex conjugate to cn, right? And here, xn, y1 complex conjugate to c1, xn, yn complex conjugate to cn. So actually you can factor it out. So here, x1 is a common factor, and xn is a common factor, right? So I can move to the next page. Edit. Is it copy or add as a clipboard? Copy, I think it's copy. And then you put next page. Let's do it again. Copy as a clipboard. Oh. What did I do? Something is wrong. Oh, I should do this. It doesn't work. Maybe I have to write down again. You go there. Leave out. No, what happens? Maybe I should just clip as a clip art. Or maybe paste. No. Sorry. So I remember that. So X, Y, Z turns out to be, you remember that too, right? So X1, Y1, complex conjugate to C1, plus x1, yn, complex conjugate zn, xn, y1, complex conjugate z1, xn, yn, complex conjugate cn. And what I was doing, you can put this as x1, xn, with a common factor y1, yn, complex conjugate zn. And this is actually yz, right? So this whole thing can be written as x, y, z. So outer product and inner product are related to by associative rule. So since we learn inner product and outer product, let's do some very interesting things. Okay, say x is n by 1 vector. So we collection of vectors is called the vector space. So say if V is called the vector space, condition is if x, y belongs to V, then C1x plus C2y is also free. So vector space is sometimes called the linear space. And the definition of vector space is a collection of actually cat vectors. And if any two vectors belongs to the vector space, then their summation with some constant is also element of a vector space. And this is called the linear combination. And we call sometimes this is called lambda I is called the orthonormal basis of vector space if this is called the lambda. we are going to use some Greek alphabet here, so maybe it's good to know a few of the alphabet. Say, everybody knows this. This is called alpha, beta, gamma, delta, epsilon, iota, kappa, lambda, mu, nu, omicron, pi, sigma, rho, phi, psi, eta, psi, what else? Psi, this is called psi. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20. There must be 4 more omega, alpha and omega, 21, 3 more. Epsilon. Tau, 2 more. Zeta, zeta, 1 more. Okay, that's good enough. So we are going to use some of those alphabet. So special vectors lambda I is orthonormal basis of a vector space V if the inner product satisfies delta ij. Then so V is a vector space. Then orthonormal basis. Then we have the following properties. The outer product of the orthonormal basis is identity. And if A satisfies a self-adjoint, matrix, or the self-adjoint matrix is sometimes called the Hermitian matrix. Then we have a very important theorem. Then alpha 1 alpha n such that A can be written as alpha I as a name for the spectral theorem. Maybe you can take a break for a few minutes and continue. So I guess we can continue. There actually and basis such that the spectral theorem is so if the lambda is a orthonormal basis, then the sum of the outer product is identity matrix. And special case, if A is A adjoint, it's called self-adjoint or Hermitian matrix. If A is a self-adjoint, then there exists a set of real numbers, alpha 1 to alpha 1, and the orthonormal basis, lambda I, associated with A, such that A can be written down this way. It's called spectral theorem. So this is actually a very powerful theorem. But too abstract. Think about it, right? So example. Consider the following vectors. Well, actually, there is a reason, but so 1 over square root of 2, 1, 1, lambda 2 is square root of 2, 1 minus 1. So how about lambda 1, lambda 1? It's square root of 2 is 1/2, right? 1, 1, 1, 1. So we have 1, right? But lambda 2, lambda 2. Square root of 2, 2, 1/2, right? So 1/2, 1, 1, 1 minus 1, 1 minus 1. So it is 1. Lambda 1, lambda 2. 1/2, 1, 1, 1 minus 1, which is 0. We can interchange the order. Lambda 1, 1 minus 1, 1, 1 is again 0. So this lambda 1, lambda 2 are actually orthonormal bases, right? So this is this property is actually holding for any orthonormal basis, but I can move on to the next page. So Remember that? 1/2, 1, 1, 1, 1, 1/2, 1, 1, 1 minus 1, 1/2, 1, 1, 1, 1, 1 minus 1, minus 1, 1, right? So if we add them together, what happens? 1, 0, 0, 1. Identity. And actually, this orthonormal basis is associated with this matrix. So, where is this A? With alpha 1 is equal to 1. Alpha 2 is minus 1. Let's check. And we are going to learn why this is, but right now, just believe me. Just try alpha 1 is 1, alpha 2 is minus 1, and see what happens. So, plus 1, lambda 1, lambda 1, minus 1, lambda 1, lambda 1. Plus 1, we have, you remember the formula, 1/2, right? 1, 1, 1, 1, minus 1, 1/2, 1 minus 1, 1 minus 1. So 1/2, 1, 1, 1, 1, plus 1/2, minus 1, 1 minus 1, minus 1, 1. But since we have minus 1, we have what do we have? 0, 1, 1, 0, right? Which is A. It's interesting, right? So I can summarize. You may need some time to copy. How can I? So if for A we set lambda 1 as and alpha 1 equal to 1, alpha 2 equal to minus 1, then one property, right? Lambda 1 plus lambda 2 is equal to identity, and plus 1 lambda 1 plus minus 1 lambda 2 is A. So some particular symmetric matrix or Hermitian matrix, we can associate a set of numbers alpha 1, alpha 2, and basic vector lambda 1, lambda 2, and then obtain that the summation of an inner product of an outer product is identity, and the summation of the outer product with the particular numbers alpha 1 plus alpha 2 gives a Hermitian matrix. So actually it has a name. This is called completeness. This is spectral theorem. So before we start the general properties, I like to spend some time on the examples, so to make you familiar with the concept of the spectral theorem. And can I move on, or still it's time to copy? Not very difficult, right? If we can choose another example. This is also symmetric, right? Hermitian. In this case, choose lambda 1, 1, 0, easiest one, lambda 2, 0, 1, alpha 1 plus 1, alpha 2 is minus 1. Let's check. And actually, this is just, I just choose particular bases and numbers, and I didn't explain why I have chosen these numbers, and we're going to get there later. But it's just an example. Let's see the particular combinations. So lambda 1 is actually what? 1, 0, 1, 0, it's 1, 0, 0, 1, 0, right? Lambda 2 is 0, 1, 0, 1, 0, 0, 0, 1. So obviously, lambda 1 plus lambda 2 is 1, 0, 0, 1 is identity, right? And plus 1, lambda 1 plus minus 1, lambda 2 is 1, 0, 0, minus 1, it's A. Third one, I'm going to use, let me just use Pauli matrix. Another matrix. So let's just try 3 examples and study the more general properties. Oh, it's complex numbers. Let's see if it is a Hermitian matrix. So what is the transpose? If you make a transpose, row become column, column become row. So this is 0i minus I0, right? So a joint A transpose complex conjugate 0 minus I 0 is A. So this matrix is Hermitian. And for this matrix, let's choose lambda 1 square root of 2 1I lambda 2 square root of 1 minus I. Oh. And we need to check whether this is a orthonormal basis. So lambda 1, 1 half. When you make a bra vector from cot vector, you make a transpose and complex conjugate. So it will become 1 minus I, right? 1I. So I times minus I is 1. So this is 1. Lambda 2. Again, 1I, 1 minus I is 1. Lambda 1, lambda 2. One half, 1 minus I is 0. So they have orthonormal basis. And let's check if they satisfy the completeness and spectral theorem. So lambda 1 plus lambda 2 is 1 half, 1I, 1 minus I, 1 half, 1I, 1I, right? So it becomes 1 half, 1 minus I plus 1, 1 half, 1I minus I, 1. Amazingly, if we add them together, even though the two matrices contains imaginary part, it becomes I, right? How about the second property? Plus 1 minus 1 so 1 half is 1 minus I 1 minus 1 half 1I minus I 1 becomes 0 minus I 0 is A, right? So for given symmetric or Hermitian matrix, we can choose a set of orthonormal bases and also alpha and alpha numbers, such that they satisfy both completeness and secondly spectral theorem. So we have seen that for 2 by 2, but this property is generally hold for any n by n. So I'm going to just repeat the previous statement again. Why we are doing that, we will see soon. Okay, so given Hermitian A exist. Given n by n such that sum over I is equal to completeness, and alpha I spectral theorem. So why we are studying spectral theorem? It's obvious. Okay, we can calculate a square. Say a times a, right? Which is using spectral theorem. Alpha I, alpha j, we have seen that the product is associated before. So if you multiply them together, then you can make a new product with this first. And we know that this is delta ij, right? Because it's orthonormal basis. So it becomes obviously this term can be written down as now we have alpha I, alpha j, lambda I, delta ij, lambda j, right? I mean, if you go from this, but delta ij is 1 when I and j are the same, and 0 when I and j are different, right? So it can be written just a simple way: I equal to 1 to n alpha I square, lambda I, lambda I. And then you can actually continue. A to the k is simply alpha I to the k. So actually, if A is a n by n matrix, and if I ask you to multiply them by k times, if you do term by term, it takes a very long time, right? But using the spectral theorem, you only need to calculate this output product once, and then multiply by the coefficient. That's sum it over. Just do it once. So you can do it tremendously faster than this kind of calculation. And for example, let's go back to the case. So this is very interesting thing. You can calculate the matrix product or matrix to the k, a to the k, by simply expanding the spectral theorem and sum over the spaces once. For example, let's go back to A example. Zero, 1, 1, 0. Then we know this lambda 1 is square root of 2, 1, 1. Lambda 2 is square root of 2, 1 minus 1. Alpha 1 is plus 1. Alpha 2 is minus 1. And of course, so outer product lambda 1. Lambda 1 is 1 half. 1, 1. 1, 1 is 1 half. 1, 1, 1, 1. Lambda 2 is 1 half. 1 minus 1. 1 minus 1. 1 half. 1 minus 1. Minus 1, 1. Okay, I can ask you to calculate 8 to the 100. If you don't know the spectral theorem, what do you have to do? Just multiply this matrix 100 times, right? Of course, it's a very simple calculation by taking 100 times the figure of it, right? So, if you don't know the spectral theorem, then you're going to do this. Times, right? Of course, you can do that. Well, you can do that, but it takes some time. Because matrix multiplication takes time. 100 times, maybe if we take 100 times, if we take 1 second for each product, maybe 100 seconds, then it's about 2 minutes. But since we know this already, right? So on that versus, we can just do this. 1 to the 100 minus 1 to the 100. We know the answer already, right? So what is minus 1 to the 100? 1. So the answer is I. So you can do it in 2 seconds. Or okay, so what is A to the million and one? A to the million and one. Of course, you can multiply them together, right? Billion times. Billion and one times. So if you do that by hand without the knowledge of spectral theorem, how long will it take? If each time takes 1 second, so million multiplication takes billion seconds, right? So 1 million second is how much? 1 hour is 3,600. So 3,600 times 300 is close to 1 million, right? So 300 hours. So 1 day is 24 hours. So if you multiply this matrix without sleeping, it takes about 300 hours. So it's 2 weeks. So even though A is very simple matrix, if you need to multiply million and one times, it takes about 2 weeks. But you can actually, because now you know the spectral theorem, you can do this. Minus plus 1 to the million and one times lambda 1 and lambda 1. Minus 1 to the million 1, lambda 1 and lambda 1. So what is the result of plus 1 to the million and 1? This is 1, right? How about minus 1 to the million and 1? We know this minus 1. So this is A. We know the answer. We can write down in 2 seconds again. So instead of multiplying this matrix product for 2 weeks, you can get this result for maybe 1 or 2 seconds. Or I can be even a little bit more vicious. $100 million. How long will it take? The 100 million seconds. That's how many hours? So 1 million seconds is about 300 hours, right? So 100 million seconds is about 30,000 hours. So if you divide by 24, it's about a little about 1,000 days, 3 years. So if you multiply this matrix 100 million times, it will take 3 years, right? But since we know the spectral theorem, we know the answer already. It is simply A. Spectral theorem also allows the define matrix functions. For example, if matrix function is defined as identity plus, say, A1, A2, A square, AN, then using spectral theorem, it is simply this. A1, A alpha I, blah, 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 plus AN, alpha I to the N, lambda I, plus. So we can actually put them together into simple expression is 1 plus A1 alpha I, A2 alpha I square, AN alpha N square, lambda I, and this can be written as F alpha I so matrix function can be defined. So we can define exponential matrix or something like that. So spectral theorem also allows to define the matrix function. And maybe we can stop here today and continue to next week. So next week we are going to find the condition, under which condition that those particular root number basis set and also the real number set can be found for given summation matrix. Okay, enjoy your lunch.